Okay, so today we have Byrnes from Sussex who talk about the current state of the Curvaton scenario.
Right. Oh, thank you. Thanks for the invitation to come here. And yeah, sorry I'm only staying for a few more hours, but I teach tomorrow morning, so I have to fly back tonight. It's a pity. Anyway, here's just a picture from near Sussex University in Brighton, which is where I work, just to show you. It's got nothing to do with the Curvaton. And my most recent paper on this topic was with Marina Cordes and Andrew Little from Edinburgh University. But there's numerous older papers. And just by good luck, we were after the bicep result, which made everyone crazy for a while. Now it's all got a bit less crazy. Let's compress it less. So, for those who weren't here just 15 minutes ago, what is the Curvaton? The Curvaton, it's an alternative model to the standard model of single field slow roll inflation, in which you need inflation, so you have an inflaton field to expand and accelerate the universe. And you have now a second field which generates the curvature perturbation, generates the perturbations, hence called the Curvaton. So, depending on your taste, this is either a good thing or a bad thing. It liberates the inflaton because you no longer need the perturbation spectrum, which you observe very well, to be generated by the inflaton field, at the expense of making things less predictive, because now you have 2 degrees of freedom instead of 1. Or as we were discussing earlier, potentially you have lots of inflatons, lots of curvatons. You could have lots more freedom. Specifically, as opposed to just generic, I have inflation with multiple fields, the Curvaton should be subdominant during inflation in terms of its energy density, so that we have an inflaton driving inflation and the Curvaton generating perturbations. The Curvaton, I'll show you in a second why it should be long-lived, meaning it decays long after the inflaton has decayed. And thirdly, generates the curvature perturbation, which is where the name comes from. However, I'll often drop this third assumption and allow both of the fields to generate the perturbations to some level. And why is this interesting, apart from the fact that high-energy physics might or might not require us to have multiple fields, and this is an ongoing debate among SUSY and string theory people, whether we want loads of scalar fields or just one, or... Yeah, there's no agreement that I'm aware of. Is that nonetheless we can ask ourselves the question, if there was another field, how would we be able to observe it? Does it make any difference? And potentially there's lots of new phenomenology to get out of it. So for example, local non-Gaussianity. I'll introduce this in more detail later, but it just says that there may be information beyond the 2-point function. So the higher order correlators may be non-zero. Then isocurvature perturbations, meaning that different parts of the universe may be perturbed differently. So in some we may have a larger, say, perturbation from dark matter, and in another larger one from radiation. Then generically suppress the tensor to scalar ratio, which is why after bicep this seemed interesting, because bicep was saying no, we have a large detection. I'll come back to this. Now, none of these 3 things have been observed. So observations don't require a Curvaton. But as I said, we should still ask ourselves, and high energy physics might, some people tell me, require multiple fields. Well, there's a local twist here, which is, right, Martin is one of the first sets of the 3 papers on this topic, back from 2001, so this is getting fairly old now. And it's up to about 1,000 citations, the model. There is also some earlier work, which is not the Curvaton, but somehow related in spirit, by Linde Mukhanov and Mollarach, from even earlier. Okay. Now the Curvaton is what I'll focus on, but I just want to say everything I'm going to tell you today could be thought about in terms of other models which are related but not the Curvaton. So there's a model of modulated reheating, which is after inflation has ended, the universe is cold, it's empty. You need to recover a radiation-dominated universe. And another way to do it from the Curvaton to create perturbations is instead to say that the efficiency of reheating, or the temperature of reheating, is a function of where you are. So in some spots you reheat more efficiently than in other spots. Or maybe when the time when inflation ends is a function of position, known as inhomogeneous end of inflation, you get very similar phenomenology. Or simply multiple field inflation models, where one field becomes more dominant or less dominant while inflation is going on. You have some curve trajectory in field space. All three examples create something related to the Curvaton phenomenology. It's not a coincidence. One can go into great detail why they're all mathematically related, but nonetheless, physically, they are different scenarios, and the detailed predictions are different. And for simplicity, I'll focus on one model for this talk, which is, I think it's fair to say, the most popular of them all, partly because it's probably the easiest to do the calculations in that case. And it's perhaps also the original, in which detailed calculations were carried out. So we were just looking at this power spectrum from Planck. This is the newest data until in a few weeks' time we'll get the new data. And we see this amazing amount of structure in the two-point function. This is a two-point function as a function of scale on the sky, or multipole number, from the very largest scales out here to the smaller scales over here. And notice we observe something like a range of, well, 2 orders of magnitude in terms of scales. And in all of this detail, these are data points with error bars which are minute. You can fit all of this with just 2 numbers. You need an amplitude of the perturbations and a spectral index, and that's all. So you fit all of the structure with multiple peaks with 2 numbers. And that for me is quite amazing. It's an amazing compression of data. You have the sky with something like 50 million pixels, in which you can get a reasonable signal to noise in each single patch. And you want to describe all of the statistical properties of correlating all patches across the sky in every possible way. And what do you need to do? Well, you need a background cosmology model, which is quite simple, lambda CDM. And you need 2 input parameters. You say that there are only Gaussian perturbations with an amplitude, and a spectral index which describes the function of scaling, and that's it. And you get everything out. Modulo some anomalies, which are not highly significant. So you can only do this massive data compression if the perturbations are Gaussian, if everything is in the 2-point function. And if that's true, then by Wick's theorem, all the higher order correlators reduce to the 2-point or are 0. So why? Well, are the perturbations Gaussian? The constraints say they're not very far from Gaussian. They're at least 99.99 or so % Gaussian. There's still room for some non-Gaussianity, and we'll see what that means in terms of the Curvaton. But why might it be Gaussian? Well, often it's a central limit theorem. Here, for us, it's the perturbations, sorry, it's not come out very well, of the ground state of the quantum simple harmonic oscillator are Gaussian. And so if the perturbations we see are from the Bunch-Davies or the ground state of the vacuum oscillator in de Sitter space on very small scales, which are then blown up through inflation to match the larger scale perturbations in the universe, you would expect them to look Gaussian. There are some caveats to this which I'll come to, but that's at a background level why when people talk about the simplest single field models, they say the perturbations should be Gaussian. To very high accuracy, much better than the observational accuracy. Now let me finally get to a few equations about the Curvaton. First of all, let me take the simplest possible thing, which is just to give it a mass and ignore all the self-interactions or interactions to other fields, which during inflation may well be a very good approximation, although obviously eventually it will need to couple them to decay. So the equations of motion for my Curvaton field, sigma, here's my background equation of motion, and for the perturbations on the large scales. And if I had just this quadratic potential, so just a mass term, you can trivially see that you get exactly the same equation of motion, both for the background and for the perturbations, which creates a wonderful simplification in the equations.
Sorry, this is the first time I hear about it. This is a real scalar field. It's called.
Right, yeah. So it just has a base.
What we need a potential to get.
Yeah.
And then it's not Gaussian anymore.
It actually is, because the perturbations are around, it doesn't need to be around the minimum. It's not completely Gaussian, but it's close to Gaussian. We'll come to that very shortly. Here I just want you to see that you have the same equation of motion for both if you have a quadratic potential. I am neglecting things like the back reaction from gravity in this equation for the perturbations, but that's fine at this level. Because remember, by definition, the curvaton is very subdominant compared to the other fields. So it's not having a strong gravitational influence on the universe. Yeah.
So which one should be the physical interpretation of this field that I should keep in mind?
Of the curvaton?
Yes. So is it like coming from high energy physics? Is like a scalar, or it's something? What do you call it, curvaton?
It's a scalar.
Which one is the? Why do you call it like that? Curvaton.
Because it will generate the curvature perturbations.
Okay. So it's not related to the conformal factor of the metric or something else.
No. It's just a simple scalar field, which is going to be derived to have the curvature perturbation, generate the curvature perturbations by making its properties suitable. So in terms of a particle physics, so we come to that here first of all. So if you think about the density perturbations within slow roll inflation, the kinetic term is very unimportant in terms of its energy density. So the energy density is nearly all in the potential term. The potential term we were assuming is quadratic. So if I work out what is delta rho over rho, well, it's V of sigma plus a little perturbation minus the background, V of sigma divided by the background, just to get a dimensionless ratio. And this is delta sigma over sigma plus delta sigma over sigma squared. Okay. So that's what we get, assuming a quadratic potential. And because we assume quadratic, there are no higher order terms. We can stop here.
Could you repeat why the kinetic part was subdominant? Because it's subdominant for the inflaton because you want the right equation of state.
That's right.
But you don't have that constraint in the curvaton, do you?
You don't have it, no. But what you do need in practice is for the curvaton field to be light anyway. Because you want it to be frozen for a long time. That's actually coming up in the next slide. You're right, a priori. You're not killing inflation if you give the curvaton a big mass. And then it might not be rolling slowly down the potential, but it might go down quickly. However, then it will be of no use for generating the curvature perturbation. Basically because if it was rolling quickly, the perturbations which come out would not be close to scale invariant at all. And we have observed that they are. So you need it to be light compared to the Hubble parameter, which means it's frozen in just like the inflaton is frozen in. But yeah, in a sense you could say that's an additional fine-tuning because that wasn't forced on you to create successful inflation. For the inflaton, you were forced to do that. Yeah. But again, when I said some string theory people say you need lots of light scalar fields, and so then they would all have a mass less than Hubble rate. But some don't. Some say you have none. Some say you can't invade the Sitter space in string theory. So I'm not using any of that for motivation. I'm just saying if we have this, if it's light, what are the consequences? If it's heavy, the consequences are that the perturbations are not close to scale invariant. So it doesn't match observations. And then we stop. So these were the perturbations. So you have the Gaussian. Well, given the argument I've given before, the perturbations itself of the curvaton delta sigma should be close to Gaussian. But now you see delta rho over rho is not Gaussian because you have a Gaussian plus the square of a Gaussian. And this is already introducing what I will call local non-Gaussianity, which I already wrote on the blackboard earlier. Now, if this was it, then the coefficient of the second order term to the first order term is of order unity. However, we should be careful here that this is a density perturbation of the Curvaton field relative to the Curvaton rho sigma. What we really observe is the perturbation relative to the total background energy density, which is not just the Curvaton but everything else. So the curvature perturbation, which is like delta rho of rho total, is the energy density in the Curvaton compared to the total times the curvature perturbation due to the Curvaton field itself, relative to itself. So then we have the perturbations are suppressed by some fractional energy density of the Curvaton to the total. So that's what's given here. And then if you plug that into here, so my total perturbation is omega sigma, the fraction to the total, you'll find that FNL, which is, well, I'm coming up more in the next slide, but it's the ratio of the second order term to the first order term squared. It goes like inversely proportional, so 1 over the energy, fractional energy density. But first to answer why, some of the obvious questions like why does the Curvaton need to hang around for a long time? What's it doing? Well, that comes up in this plot. So this is a function of time or of scale factor along the bottom. So here inflation is going on. And the red line is the inflaton or the decay products of the inflaton. The blue line is the Curvaton or the decay products of the Curvaton. Okay, so during inflation the inflaton is dominant, here's density, and the Curvaton is subdominant. Then at some point inflation ends, and just for simplicity I'm assuming the inflaton immediately decays to radiation. So the inflaton, the Hubble parameter is roughly constant during inflation, energy density isn't decreasing, then it goes to radiation, and so the energy density decreases like a to the 4th power, a to the minus 4. So they start shooting down. The Curvaton, on the other hand, initially, by assumption it was light. The mass is much less than the Hubble parameter, so initially it will stay frozen, even when inflation ends. It stays frozen until its mass becomes of order the Hubble parameter, and then it will start to oscillate. And when it oscillates in a quadratic potential, its energy density, you can check this, decays like matter. So it goes like a to the minus 3, while the background goes like a to the minus 4. So the inflaton energy density, or the radiation it's decayed into, is going like a to the minus 4. The Curvaton's going like a to the minus 3, and you can see the background energy density of the Curvaton relative to the inflaton is increasing, like the scale factor A. So if it decays late, meaning it keeps oscillating in its quadratic minimum for a long time, it's going to get more and more important. And if it hangs around for long enough, it will become dominant. At some point it needs to decay. It certainly needs to decay before nucleosynthesis, but there could be a very, very long time in terms of energy scales between the end of inflation and nucleosynthesis. So during this time the Curvaton is becoming more and more important, and we don't know how much. It might become dominant, so omega sigma would equal 1, or it may stay subdominant. But from observations we'll see it can't be too subdominant. So there's this unknown factor here. When does it decay? Before or after it's dominant? And that's one of the observational parameters we can constrain. Any questions on the background? Yeah? No? So non-Gaussianity, I'll just say a little bit more. So here is a definition of so-called local non-Gaussianity. So in every pixel of the sky or in every patch, you model the perturbation as coming as taking sampling from a Gaussian random field plus a little bit from a correlated square of the Gaussian. And then times this unknown amplitude FNL, which I've already shown you what that would be for the Curvaton. And in terms of observational constraints from Planck, this is by far the best constraint we've ever had. It's 2.7 plus or minus 5.8, which might not sound that tight, but when you consider the second order term as of order, the power spectrum, which is 10 to the minus 10, the linear term is the square root of the power spectrum, 10 to the minus 5. It means that the second order term, even if FNL was 10, is much, much smaller by many orders of magnitude compared to the linear term. So the perturbations are close to Gaussian. It's just a question of how close. On the other hand, notice that FNL of order unity is certainly still completely allowed by the data. And we'll see that's an interesting level to search for with the Curvaton model in mind. I'll leave the rest of the details. So if we do the full calculation for FNL from the Curvaton, what you get, including back reaction from gravity and everything else. So FNL, it depends on this R decay parameter, which is the ratio of the Curvaton to the inflaton decay products in radiation plus the Curvaton decay with some appropriate factors due to the different equations of states of matter and radiation. Don't worry about the details. Importantly, if FNL will be large, then omega sigma is small, and R decay is very similar to omega sigma. They're either both small or both of order 1. So either FNL should be large, and in fact positive, because we have a positive sign out here, and that's already tightly constrained. FNL is less than 10. It couldn't, a priori, it could have been 10 to the 5, 10 to the 4. So the point constraint tells us that R decay is bigger than roughly 0.1. Goes like 1 over. Okay. So we know if the Curvaton existed, it was at least 10% of the background energy density at the time it decayed, which is a lot more than it needed to be back when Martin was working on this, right? 15 years ago. Then it could have been maybe 1 part in 10 to the 5. Now it's more like 10%. On the other hand, if it's dominant, then FNL, we have a very precise prediction. R decay here goes to 1, and FNL is minus 5/4. So that's, in a sense, an attractor solution, because if you think back to this plot, if the Curvaton simply hangs around for long enough, it will become dominant. Once it's dominant, it's dominant. It doesn't matter how much longer it stays dominant. Omega sigma is 1, and FNL will be minus 5/4. So given where we know we already are based on the data, I would say if you have to predict one number, you'd have to say FNL is minus 5/4, which is consistent with Planck, and in fact very hard to measure, because look, the error bar will need to get a factor of 10 smaller before we can test that, which is going to be very high. So what does it predict? Well, I've already been getting into this, right? FNL is between minus 5/4, and it turns out it can't be more negative than that. But it could be more positive, and as much more positive as you want. So in terms of a linear scale on FNL, 99.99% has already been rolled out. But the interesting part around 0 is still left. Well, interesting or boring, depending on your perspective. On the other hand, in terms of a linear scale on R decay parameter, only 10% has ruled out. It has to be at least 10% of domination, and consistent with domination. So, given what we had a priori, either FNL is large and positive or minus 5/4. Given the data today from Planck, you'd bet on it being minus 5/4 and the Curvaton being dominant. Okay. And just to drive that message home, here's a plot of the Curvaton decay rate, gamma sigma, which you should compare to the Hubble parameter at the time it decays. Basically, it will decay when gamma equals h. Then, well, basically if gamma sigma is small enough, R decay will become 1. And if it's really small, like 10 to the minus 30, it will still just stay as 1. It's an attractor in that sense. And that's by my master student, who's been making me lots of nice plots. That's cool. Now, I said I was going to drop one of the assumptions of the initial Curvaton, but stop me if I'm going too quickly. If not, I'll drop one of the assumptions and ask us the question, well, what happens? Why did we neglect the inflaton field perturbations? A priori, every light field is perturbed in de Sitter space. And in fact, they're all perturbed with the same amplitude of perturbations of order the Hubble parameter, which is your only energy scale in the problem. Okay. So the inflaton is perturbed, the Curvaton is perturbed, because they're both light. So now let's calculate what is the power spectrum of the inflaton. The inflaton is phi here, and the Curvaton sigma. The inflaton goes like 1 over the first low roll parameter epsilon, which we know this 1 over epsilon should be at least 100, if not bigger, times the Hubble parameter squared. For the curvaton, it goes like this omega sigma parameter, which remember was less than 1, times 1 over the sigma field average value during inflation, times h squared as well. So they both go like h squared. So changing the energy scale of inflation doesn't change anything. They both rescale exactly the same. However, this term 1 over epsilon is large, omega sigma is small, so what we need for the curvaton is for it to have a small field value, a small value during inflation, small compared to the Planck scale. So if it's of order 10 to the minus 2 or so, then you're fine. And this could be large compared to this term. The total of both of them, and what we observe is the total curvature perturbation, must be of order 10 to the minus 10. But we can always do that by rescaling the Hubble parameter. What's interesting here is the ratio of the two terms. And then we can ask, well, what happens now to non-Gaussianity? It turns out the inflaton field perturbations have to be extremely close to Gaussian. So the only non-Gaussian source is the curvaton. You can then calculate the 3-point function, which is what we call the bispectrum. It's only due to the curvature, curvaton perturbation, sigma, and it goes like the square of the power spectrum of the curvature perturbation due to the curvaton divided by omega sigma. However, this is probably a bit fast. FNL is the power spectrum, sorry, the 3-point function of the curvature perturbation divided by the square of the power spectrum. So that's the bispectrum, which is the same as that of the curvaton because it's the only non-Gaussian field in your problem. So you get 1 over omega sigma times the power spectrum of the curvaton to the total squared. And this fraction here should be less than 1 because the power spectra are always positive. So when you add a new source of perturbations, you're adding a new term, which is positive, it's additive. I am assuming the inflaton and the curvaton perturbations are uncorrelated, but that's really fine. It's nearly impossible to correlate them, because unless you couple the fields, which I'm not doing. Okay. And the tensor to scalar ratio is also reduced. It's reduced by how much the inflaton field perturbations are suppressed compared to the total. So in the pure curvaton limit, where the inflaton field perturbations are completely negligible, the tensor to scalar ratio is also negligible. That's where bicep would be exciting. It would be saying that curvaton cannot be producing the full perturbations. Any questions? No. So, let me quickly go a little bit into higher order. So if, last time I truncated at second order, but imagine if I didn't truncate the potential, the curvaton field potential at second order, and allowed it to go beyond the quadratic, things get a lot more complicated, but then I should include a third order term and higher orders, because now I could have sigma cubed, sigma to the 4th power, etc. Right. So here I can't truncate anymore, if I don't have a quadratic potential. So now the next order non-Gaussianity term, the GNL, which gives me a 4-point correlator, would also not be 0. GNL is really hard to constrain. Planck haven't produced a constraint yet. And strangely, no one else has either with Planck data. From WMAP, we know GNL is lesser than of order 10 to the 6. So it's quite a weak constraint compared to FNL of order 10. It's 5 orders of magnitude weaker, but the reason is because it's multiplying a term, which is the Gaussian perturbation cubed. And remember, the perturbation is of order 10 to the minus 5. So it's multiplying a very, very suppressed term, making it very hard to detect. Now, I think in view of the time, I'll skip this and rather go on to isocurvature perturbations, which I think is more interesting right in this moment, waiting for Planck, which is cosmological perturbations may be of 2 types, adiabatic or isocurvature. Adiabatic means locally the universe looks the same everywhere. You have the same ratio of dark matter, of baryons, of photons in all different parts. Isocurvature instead could mean you have the same density everywhere, But wherever you have more dark matter, you have less photons to compensate. But the total energy density is the same. And we have good constraints on isocurvature, well, quite good constraints, from Planck, and we expect them to increase a lot by the end of November. And the Curvaton, because it's a multiple field model, if you have two fields generating perturbations, they could be decaying at different rates into radiation and dark matter, and then the universe would have an isocurvature component in it today. It's not required. If the universe thermalizes when the Curvaton decays, then you get rid of the isocurvature, but it could still be there. And Planck data should significantly improve the constraints this year. And regardless of what comes out, theorists are not really ready. We don't understand reheating well enough to interpret the constraints in terms of real models. So for me, whatever happens, even if it's the maximally boring universe, we should interpret what the constraints mean properly. And that's a big work which is still left to be done. Now I'll get into a little bit this new paper I did with, well, newish paper from this year with Cortes and Lidl, where we looked at a specific model where you have a quadratic inflaton and a quadratic curvaton, just to keep things simple. Going back to a model from Andrew and Nicola Bartolo from 2002, and back then basically anything was allowed. They had to make many sort of ad hoc assumptions. We could now go back, revisit with Planck data, and drop nearly all of the assumptions they made and still get tighter constraints. Okay. So we're going to release a lot of the assumptions and see what's allowed. And to do this, we mainly look at the effect on the spectral index, NS, which, as I said, has now been observed not to be 1, which corresponds to scale invariance, where the amplitude of the power spectrum is the same on all scales. Instead, we know it's bigger on the larger scales by a few %. And on the tensor to scalar ratio, where we have an upper band, and this is the 1 and the 2 sigma contour from Planck, and we see that pure quadratic inflaton, which are the black dots in this plot, there's a little bit of uncertainty depending on how long inflation lasted, which scale do we match to the horizon scale today. Don't want to go into the details, but it's a bit of uncertainty, not much. The tensor to scalar ratio is roughly at the 2 sigma upper bound for a single field inflation with a quadratic potential. In the pure Curvaton limit, you come right down, you suppress the tensor to scalar ratio, and you come down to here. And the spectral index constraint also changes. You move along either these red or these blue curves, depending on what is the mass of the Curvaton. The red curve is where the Curvaton is almost massless. The blue curve is where it's as heavy as we dare to make it while still trusting our calculation. So you have some certainty along here. And in the mixed case, where the inflaton perturbations and the Curvaton perturbations both generate, add to the total, significantly you move anywhere along this line, between the Curvaton limit down here and the inflaton limit at the top. And there's one more case, which is these green lines. I haven't talked about them, but that's if you had 2 steps of inflation. You have the inflaton field, then it decays, and then the Curvaton is so high up its potential that before the Curvaton decays, it drives a second period of inflation. Basically, the curvature VEV is high enough to drive a few e-foldings of inflation by itself. And then the prediction is that the tensor to scalar ratio stays at the same level as single field quadratic inflation. But the spectral index can become a lot more red. So you can go way off this plot. However, it's no longer favored by data at all. That was the situation until luckily we were so slow finishing this that the bicep data came up first. Really, that was just luck. We didn't know what that was happening. And bicep said we've protected R. In fact, it said it was somewhere at the level of 0.2, plus or minus 0.05. So something like the lower bound was of order 0.1. And if that's true, and in the meantime there's lots of reasons to be highly skeptical because of dust modeling, which they really did wrong. But if that would be true, then the tensor to scalar ratio is bigger than of order 0.1, meaning that the original Curvaton scenario, where the tensor to scalar ratio was negligible, has been ruled out. Instead, you're forced into a scenario where you have significant amount of perturbations from the inflaton. So you're somewhere up here, not too far away from the single field inflation limit. You can relax these things a bit by playing around with your inflaton and Curvaton model, but the basic conclusion stays. The pure original Curvaton scenario would be ruled out. However, it's much more likely that the bicep data is wrong. But time will tell. So this is potentially a difficult time for Curvaton fans. Well, the bicep detection is probably not correct, but we have to wait for the joint Planck and bicep data, where they can both control the dust foregrounds and have a high sensitivity of beam mode polarization. Now you can talk to Martin about a model where you get a large running of the perturbations of the spectral index from the Curvaton, or you can have anti-correlated isocurvature modes, anti-correlated to the adiabatic perturbation to suppress the scalar perturbations on large scales. There's some observational hints that we need to do that. Planck did significantly constrain non-Gaussianity and isocurvature modes, both of which potentially are there from the Curvaton, but it's not at the level where you've ruled out the Curvaton. However, for the simplest Curvaton, right, none of these lines really go into the 1 sigma region anymore. And with the new data, we should, reduce these contours, and we may start to rule out the simplest scenario. That's not the Curvaton scenario, but it's the simplest realization, where we specified the inflaton modulus. Right, so these lines, we have to be somewhere on these lines. If this would shift a little bit left, or if the contours, say, shrunk by a factor of 2 into here, you could start to be, everywhere on this line might start to be, say, 3 sigma out. But time will tell, and I'll certainly remake these plots when we have new data. So why is the Curvaton still interesting, although we don't need it? Well, if you think we have inflation, right, at a known but very high energy scale, probably, and then a lot happens between inflation and nucleosynthesis. So, right, we had different phase transitions, we had baryogenesis, maybe magnetic fields are generated, who knows? And in all of that time, there's really very little we know. And during this time, the Curvaton may have been dominant, the perturbations might have been isocurvature, may have been non-Gaussian, and we don't know. So in all of this time, there's really a huge amount which we struggle to observe. So it's important when constructing models of the physics at this time that we realize how little we know about the background model even during this time. It's only after nucleosynthesis that we can start to really say we have a standard concordance model of cosmology, which we have observational evidence for. So will we ever learn the truth? Well, I've stressed, the Curvaton scenario really is different. It's not an order epsilon correction. It's really a different scenario. We have a second perturbed degree of freedom. Between the end of inflation and the Curvaton decay, we may have a completely different background equation of state, etc. So what was the background equation of state, say, during baryogenesis? We have no idea. And did isocurvature perturbations ever exist? Again, we don't know. Are the perturbations on these small scales, meaning the horizon scale, 1 second after the Big Bang, close to Gaussian? No, nobody knows at all. The reason it's hard to say today is because the amplitude of perturbations is so small. That FNL of -5/4, remember that corresponds to 10 to the -5 sort of order perturbation on the already small perturbations of order 10 to the -5. So it's a very hard thing to measure. It's not a fine-tuning. Well, it wasn't me, but people like Martin, they didn't say, how can we make another model which looks exactly like single-field inflation? Right, that wasn't what they were setting out to do. It just turns out it looks similar, given the observational error dies. Even the very good ones from Planck today. So they're hard to distinguish, not because of fine-tuning, just because that's the way it is. So if you have a nonlinear transformation for x goes to x plus x squared, you generate non-Gaussianity of order FNL of order unity. And order unity is small, because the perturbations are small. There's also secondary non-Gaussianity, say from gravity being nonlinear, which is of the same order of order 1. But we can distinguish the two things and tell them apart. I'm going to skip this part, given the time constraints, and get on to, so Planck, we're all waiting. It more or less has to come out at the end of the November because of the ESA official Planck conference starting on the 1st of December. So they're under a lot of pressure. In terms of non-Gaussianity, we shouldn't expect very much new. They already did a wonderful job with the first year data, and there's not that much new to be learned with polarization. The spectral indexes, the bound here should improve quite a lot with polarization data. Tensor to scalar ratio, well, we really need bicep. Apparently the joint Planck and bicep analysis is delayed, so it won't be in November, it'll be next spring, which is a pity. For many of us that's more exciting than the Planck data by itself. But there we go. Isocurvature perturbations, this is one to watch out for. Constraints are at about the percent level, but they should improve by at least a factor of 2. Some hope of a detection, maybe. And anomalies, I haven't talked about them, but there are various funny things, especially on the large scales. And it's interesting to ask, do those things persist in terms of the polarization data on the large scales, which hopefully we will reach for the first time with Planck in a few weeks. So watch out for the press release in probably the last day of November. To conclude, if confirmed, BICEP 2 has ruled out the original Curvaton scenario, in which the perturbations are purely due to the Curvaton. Even ignoring BICEP, Planck is strong enough to put pressure on the simplest Curvaton scenario, which are the plots I showed you. The above is true even if we allow an arbitrary proportion of the perturbations to come from the inflaton instead of the Curvaton, meaning that the data is now good enough to start putting pressure on even fairly generic two-field models of inflation. The one prediction we really expect from the Curvaton is non-Gaussianity at the level of FNL of order 1. Unfortunately, we're still quite some distance. Maybe in a decade with Euclid we can start testing this value. And without a detection of non-Gaussianity, or as the curvature modes, remember the Curvaton really is very different, but how can we ever distinguish them? And this is where it's up to you. I don't know. So I'll stop there. Thanks.
Questions?
So, you had some curvature based on inflaton, maybe something that is a curvature, some from the curvaton, maybe so inflation is ending, and then maybe somehow the curvaton took over for a little while. You might have some kind of isocurvature on some scales. Does that make sense? Like, but only on some scales. Is that something that people can?
At this level, if both fields are light all the way through inflation, all the perturbations should be very close to scale invariant. And then that includes the isocurvature perturbations. They will also be close to scale invariant in terms of the primordial perturbation.
Yeah, but let's say in the same scenario, the inflaton decays, and then right, but then the curvaton goes, but not till all the observable modes have left the horizon, and then it decays. So there's some overlap, but so that there's only isocurvature on. So that there would be some. I think there would be some scales where there could be isocurvature.
The horizon scale Curvaton decay is tiny. Right, it's going to be really, really small. So all the CMB scales are the same in terms of the horizon scale when the Curvaton's decaying or when the inflaton is decaying. In terms of really, really small scales, say for primordial black holes, that's true. But in terms of the CMB scales, which they're all very large scales compared to the physics operating and when fields are decaying. So in terms of the CMB, that doesn't matter.
said the simplest model, but I guess if you just generalize to monomial potential for the inflaton, basically you can probably cover the whole what is it, 2 sigma constant?
Ah, you mean this one?
Right.
If you allow yourself powers less than phi squared, so if you allow yourself, say, phi to the 2/3 or phi to the half,
But even
then
lambda 5
you can start coming down.
Yeah, but even lambda 5 won't that move you to the left?
A little bit, yes.
Yeah.
It would move you. R would be up here, but it would be a bit left, and then you would draw lines
exactly.
roughly like this. That's true. You would end up down here in the Curvaton limit, not quite the same almost, because epsilon is different.
Right.
So yeah, in fact, my master student did that,
Okay.
and the lines do something like this. So yeah, then you come into the 1 sigma again.
Then you can
In the
also
mixed case.
You can also take simple hybrid models and all.
Yeah. I mean, if you, by saying simplest, we were using the language of Bartol and Lidl from 2001 too. But yes, you're right. If you say the Curvaton plus an arbitrary model of inflation will allow me to scan anywhere along the bottom, the lower part of this plot. That's for sure.
If the Curvaton dominates, but if you then allow
Yes.
the mix, you can.
Then you can fill the whole space. Yeah. That's right. So then you can never be ruled out except through non-Gaussianity, when we can rule out fn of
Right.
order 1.
Right. So that's an interesting.
Yeah. Yeah. It's hard. You have that extra degree of freedom. And the problem is when things are really different, the length scale is so small.
No, but what I mean is when people have this thing of existing multiple inflation by non-Gaussianity, I mean, really the target is if another order 1, right? That's when you can really
Yes.
rule out the natural models of multiple inflation. Right?
Yeah, that's right. So we're talking more than a factor of 10 improvement on FNL, which is going to be hard. Yeah. Even with Euclid, to be honest, it's marginal at best. Yeah. Which I think is very non-trivial, right? A priori, there was no reason that it should be so close. But it is. Other questions?
No questions? So let's thank Chris again.